Dear audience, hope you're doing well. My name is Anas Adnan, belonging to LETSMP Laboratory of Faculty of Science of Agadir, and I'm truly honored to present to you the fruits of my work entitled Prediction of PM10 Concentrations in the City of Agadir, Morocco, using nonlinear autoregressive artificial neural networks with exogenous inputs. The plan of this presentation is the following. We're going to start with a general introduction. Then we'll describe the study area, the data collection and processing. Then we will talk about the nonlinear autoregressive neural network models and their development. And finally, we will discuss the results. Air pollutants are among the major factors causing climate change as well as negative effects on ecosystems and human health. PM10 as an air pollutant is very dangerous and harmful and has a direct impact on humans. PM10 are atmospheric aerosols particles that have the capacity to enter the respiratory system and cause significant damage. Forecasting PM10 concentrations will provide legislators and general public an idea about the future situation. However, this task remains complex given the number of parameters that directly and indirectly influence their concentrations in ambient air. Machine learning techniques have become popular in the scientific community thanks to their efficiency in modeling nonlinear and complex relationships. The aim of this study is to model and predict the concentrations of PM10 1 hour and 24 hours in advance at the level of the city of Agadir using a recurrent neural network. Our study area is Agadir, which is a city located in the southwest of the Moroccan kingdom. It is characterized by a semi-arid climate. With a population of more than 500,000, Agadir has an important economy, about 7% of Moroccan GIP, mainly based on tourism, agriculture, and fishing, which results in high density of road traffic reaching almost 2 cars per habitant. Our observation site is in Anza, an industrial zone which is one of the most populated areas in the city of Agadir and presents a lot of complaints concerning air pollution. The selection of pollution and meteorological variables as well as the study period was based on the data availability. Table 1 presents a statistical summary of the variables measured. One of the main problems most often encountered is that of missing data. Therefore, it is important to take steps to ensure the recovery of missing data. To estimate the missing values, the method of the mean of neighboring points was used. We then calculated the values of the zonal wind and the meridional wind using the following relationships, where wind x is the zonal wind, wind y represents the meridional wind, w denotes the wind speed, and phi its direction. Machine learning methods in general, and especially artificial neural networks, have demonstrated a remarkable success in different engineering fields thanks to their ability to learn spontaneously and to provide adequate and rapid results. There exists plenty of neural networks. We used in this study the nonlinear autoregressive with exogenous input neural network, shortly called NARX. Figure 2 represents the general structure of NARX. The NARX architecture is written in the following equation, where nx and ny denote the maximum lags of the exogenous and endogenous variables x and y, respectively, and yp indicates the one-step forecast of the actual value y. The function f is represented by feed-forward multilayer perceptron. RNNs are therefore only an extension of feed-forward multilayer perceptron. Unlike feed-forward neural networks, a recurrent neural network provides feedback. In other words, some output neurons are connected to neurons from previous layers, which can improve the learning capacity of RNNs and give better results. Feed-forward multilayer perceptron consists of an input layer, which receives the data to train the neural network, hidden layers, which are not in direct contact with the outside. The activation function of these layers are nonlinear in general, and the choice of its size is not implicit and it must be adjusted. Finally, the output layer, which represents the network results which are often obtained after compilation and training. Finding the RNN structure that gives the optimal results is a challenging task. This difficulty lies in the fact that no rule exists to determine the optimal number of neurons, hidden layers, or even the activation function. In this work, we have opted for four types of models: a model whose input data are meteorological variables with a time step of 1 hour, which we named NARX1; a second model similar to NARX1 but with a 24-hour time step called NARX2; NARX3 and NARX4 denote the two remaining models, which have as input data meteorological variables as well as air pollutants with a 1 hour and 24-hour ahead forecasts respectively. Table 2 illustrates the different structures of the NARX models used in this paper. We divided our database into two categories. 85% of the data were used for training the neural network, and the remaining 15% were used for testing the results. In order to train the NARX, we used the Levenberg-Marquardt backpropagation algorithm. This logistic and linear sigmoid activation functions were used in the hidden layers and the output layer respectively. In order to compare the performance of the models, several numerical indices were used to explain the quality of the model. These indices are the mean absolute error, the root mean square error, and the correlation coefficient. We denote by structure X a network of neurons with a hidden layer whose number of neurons is X. A YY structure in turn refers to a neural network with two hidden layers whose number of neurons in each of them is Y. Table 3 and Table 4 give us an idea about the performance metrics, correlation coefficient, mean absolute error, and the root mean square error of each model tested. The structure 10 gives the most optimal results for the NARX1 and NARX2. Additionally, structure 6.6 and structure 8.8 are the best ones for NARX3 and NARX4 respectively. Table 5 showcases the best performing models. In general, the results obtained by the four models are very convergent. By comparing the 1 hour ahead models, we can see that NARX3 gives the lowest MAE and RMSE with values of 5.8 and 8.57 respectively, but NARX1 gives the best correlation coefficient with a value of 19.67. And by comparing 24-hour ahead models, we notice that NARX4 gives the best correlation coefficient and RMSE with values of 93.75 and 7.09 respectively. NARX2 gives the best MAE with a value of 5.03. Figure 3 combines observations of PM10 concentrations for the first 48 hours of the test period and the concentrations predicted by models NARX1 and NARX3. We noticed that the two models failed to predict extreme values well, but in general the results obtained are close to reality with sometimes an overestimation or an underestimation. Figure 4 combines observations of PM10 concentrations for the first 48 hours of the test period and the concentrations predicted by models NARX2 and NARX4. We observe that the estimates of the two models are very close to the real values with a slightly better estimate for the NARX4 model. The two previous comparisons allow us to conclude that the air pollutants, especially ozone, SO2 and CO, are important in predicting PM10 concentrations. We notice also that the performance increases moving from 1 hour to 24-hour ahead predictions. Figure 5 shows the regression results between the predicted PM10 concentrations by the NARX4 model and the observed values. The regression line shows how much the predicted and the true values converge. Finally, to conclude why meteorological variables play a primordial role in the influence on PM10 concentrations, The anthropogenic emissions add additional information to the models, which subsequently allow better results. The four models are performing remarkably well despite the shortness of the data period, and this once again proves how efficient NARX models are. Thank you so much for your attention.